So chapter 6, we'll be looking at the population and sample. Sampling distribution. Of the mean, and in this type here is when sigma is known, and then the same thing, sampling distribution. Of the mean sigma is unknown. Then the sampling distribution of the variance. And then we have representations. Of the normal theory. And at last, we have 6.6 and 6.7. Those are the moment generating and the transformation methods to obtain distributions. Those two you may want to read them on your own, but still, they are really important to know and to get. The last two parts, I did not put them on the board. So let's start with the first one. The first that we need to look at is there is the population. And it is divided into two parts. The first one is the finite, and the one is the infinite population. So there are two types. Okay. And when we define the finite, that means this here can be counted. This here, this one infinite cannot be counted. Yeah. So in the finite in here, or the finite in here, there is the sample. So we have a population that is a finite population. And we take the sample, and the sample in here, a random sample. And that random sample is a set. Let me just put this here. You can put this as a flow chart if you want to. So the random sample is a set of observations x1, x2, x3, and so on, up to xn. And it constitutes a random sample of size n. Okay. So the sample is size n, I'll just continue in here, of a population of size n. So the small n is the size of the sample. The large N is the size of the population itself. Okay, you can write in here finite population and infinite population. So in here, all the x1s, all the x of the random variables or the random numbers in here have the same probability of being selected. So each of the x's has the same probability of being selected. Of selection or being selected. Okay. I'll extend this part in here so that it doesn't bring it here. So in here is the infinite population. And the infinite population, again, it also goes to a random sample. And that random sample is, we define it, is a set of observations x1, x2, xn constitutes a random sample of size n. Let me continue, from the infinite population. We'll define the two types of populations. But before that, I'll just continue with this. So we have, it constitutes a random sample of size n from the infinite population if there are some conditions in here. If A, each xi is random, or is a random variable whose distribution is f of x, and B, these n random variables are independent. So when we go up here to the population, where do we define whether it's finite or infinite population? It is basically defined or described by the distribution of their values, each of them. So the population is described by the distribution of their values. So it could be, when you look at the distribution, whether it is finite or infinite. When we look at how it is described, we will know whether it is finite or infinite. For example, there was a story between two people. One of them was trying to get favor with a king. So he wanted to undermine the person who's been, preferred by the king. So he told the king, "Let me ask him 2 questions." So he said, "Okay, go ahead, ask the questions." And the king wanted to know. So he told him, "How many stars in the sky?" That's infinite. That's infinite number. You cannot, define it. So the guy told him, "Okay, my king, I can answer this question. What's the next one before I answer the first?" He told, I don't know the second question what it was, but he said, "Okay, for the first one, can I go outside and come back for a minute?" He said, "Yes." So he went outside, he bought a goat, and he came back, and he told him, "My king, the number of stars in the sky are exactly the same as the number of hairs on this goat. And if this person does not believe me, he can count them." So, and for sure, the other guy said he could not do a thing about it. So sometimes it's infinite. We cannot count it under any circumstances, even if you want to. So you will take the sample, and that sample you will have to use it as a major or the main element of your study. Sometimes it is counted or it is finite. Like, for example, we have the number of students in one college. The number of students is known. So if we take a sample, that sample could be one classroom, could be one type of people, for example, who are driving to the school or who are riding the bus or whatever. That is a sample. So we take a sample based on who are the criteria, or what are the criteria that we're interested in, and based on that we define whether we are really looking at a small sample or large sample. The other idea that we want to look at is vocabulary in here. There are a few words of vocabulary that we would like to know. The first one is the inference. What does it mean? Sampling. And random, I believe that we already know what it means, but still we want to go through it. So what is inference? Any idea? So when we say inference, what does that mean? I'm going to leave it like that until you look it up. No problem. You look up this one. So you will find it, whether you look it up in the book or you look it up online, but you will find that. All right. The other one is the sampling. What does it mean, sampling? When we say sampling, it means that we're taking into consideration the population and the appropriate method used to choose a sample. That's sampling. It means that it is not just taking any sample, but the method in which we take the sample. So sampling, it is not just the word of taking a sample, but how we take that sample. We're sampling it. There are methods, and we choose the appropriate method to take the sample based on the type of population we have. As far as random, yeah, we said random, but what is random? If we want to identify or to define the word in our terms, generally it permits the generalization of results. That's what random is. Random, it means that when we use the random selection, we can generalize the result. If we don't use the random selection, we cannot generalize the results. And we talked about generalization, whether it is transferable or not transferable. What means transferable? You make a study, and in that study you think that the study can be used worldwide. It's not necessarily worldwide. It could be used only locally in one place. It cannot be used everywhere. Like, for example, if we take as we said before, the students in one college, whether they are riding the bus or they are driving, and what's the percentage and so on, and you go and you make a study. That is basically for one college. It's not for any other college. So any other college, it depends whether it is in the city or outside the city. For example, you go to Manhattan and you take any of the schools in Manhattan itself, you find that very, very few students who are driving to the school. In here, there are many students. You go outside New York City, you will find that 90% probably of students drive. So it depends on the locality. So it depends also on the research and what we are looking for. So that's what it means, transferable or not transferable. The studies, when we have a result somewhere, we cannot transfer that result somewhere else. However, if, for example, we want to know about the opinion of New York City as far as presidential election is concerned, that can be transferred. It can be used nationwide, but it cannot be used worldwide. But if we take, for example, the opinion about what is happening, for example, in France, or what happened in Turkey, or what happened in other places, like, for example, well, that opinion, it will go worldwide. So it depends on how we look at things and how we choose the topics. So when we talk about random, it is not just we're selecting randomly, but we have a goal behind that randomness. The goal is that our results can be used and they are generalized. So then we're going to be looking at this here. So we have finite population with the sample, and there is a set. I'll be eliminating this, and we write it in the conventional way. So we'll put everything while we did this. So just to understand how the distribution is. And then we introduce our functions and our equations and so on. Okay, so let's consider the following. We have the population. It has size n. Yeah. Observations. We have x1, x2, x3, up to xn. And then we have the sample. It has size n. And it is a random sample. And then we have the distribution function of, or for xi, is f of xi. For large n, for large n, or for large population in general, let me put large population. For large population, we have different situations. We're going to be looking at, I'm not going to be talking about it right away, but we will be looking at it later on, large population and small population, and what it means large and what it means small. As we said before, when we consider, for example, we consider the sample, your sample in a large population, the sample is large when it is equal or more than how much? When we talk about the sample large, it has to be equal or greater than 30. Anything less than 30 is considered a small sample. So when we talk about large sample, it has to be 30 or more. That is basically what there are some examples in the book that you may want to go through, but the essential is that we have different situations, and those situations will be presented in here. We're talking just about the population and the samples. This one here, the sampling distribution of the mean, and the sampling distribution of the mean when sigma is known, sigma is unknown. Those two here will be giving a lot of information to our talk today. So before, let me just look in here where we are as far as the examples. There are some examples in the book that we want to make sure we don't miss them. So there is on page 177 and 178, there are 3 examples. Those examples are to be read and understood, rather than there is no calculations, there is no work done in there. It's just to read them and understand what's going on in there, okay? Okay, so, and then we have the distribution when n or when sigma is, so we're going to look at the next part. This one here, the sampling distribution of the mean. Sigma is known, and that is on page 179. So they work that through an example already on page 179. But the essential, I'm giving you the essential. You may always go and read the book, it's okay. But the essential is that there is a variance. Okay. So this is 6.2. 6.2 is when sampling distribution sigma is known. So sigma is known. When sigma is known, the variance is, you have sigma square over n times n minus n over n minus 1. Again, this n here and this n, this here is population size. This one here is the sample size. This one, this again, the sample size. And this one here is the variance. The square root of the variance is equal to the standard deviation the correction factor, this here, n minus n over n minus 1, this part here is called the correction factor. The correction factor is relative to the frequency. You may want to look at that in the book. It's very well explained. Then we have the reliability of the mean as an estimated or an estimate of mu. Is often measured by the following. So this is the reliability of the mean. The reliability of the mean, is the mean close to the zero, close to the real mean or not? So it's called the standard error of the mean. So this here is sigma x bar equal to sigma over square root of n. Remember that sigma is equal to the square root of sigma square. n. In here we say sigma is known. That means it is already given. They don't ask you to calculate it or to compute it. They give it to you. Unless they give you the data and they ask you to calculate or to find sigma, that's something else. But in general, they don't do that. So the standardized mean the standardized sample mean, sample mean z, and is equal to x bar minus mu over sigma over square root of n. And later on in the chapter, this thing here will be replaced by S. I will replace it by S in here because it is the sigma, it is the, let me just write it in here. So sigma is the standard deviation of the population. So we have to make sure that we relate. When we say sigma is known, that means it is already of the population and not of the sample. When we use later on, when we use S instead of sigma, Z is equal to X bar minus mu over S over square root of N. At that moment, what happened is that the S represents the standard deviation of the sample and not of the population. So when we say S, it's for the sample. Sigma is for the population. Those two distinct things need to be really understood. So this is basically the summary of all what is given in 6.2. I just condensed everything in there. If you want to expand it, you may go to the book and read from page 178 or 179 up to 187. So you don't have to know everything, but there are some examples in there where they calculate the Z and they find the Z and so on. So it's good to know it, but it's very simple to understand it. So chapter 6 is one of the challenging chapters, but in the same time, it's one of the easiest. It's challenging to understand what's going on. But as far as the work, we already passed through the work in chapter 4 and 5. So there is no much addition to that except some formulas. 6.3, this is 6.2, sigma is known. 6.3, sigma is not known. That means we're looking at the sampling distribution of the mean when sigma is not known. How the mean is distributed when sigma is not known. In here, this is where the mean is related in here. This is mu. So for 6.3, we have the following. Sigma is unknown. Since sigma is unknown, that means we use the sample to find or to identify the standard deviation. The standard deviation in this case is represented by S. Okay, so it's represented by S. So and Z the distribution is represented by t. So instead of saying z, we're going to say t equal x bar minus mu over, instead of saying sigma, we're going to say s over square root of n. Again, n, as it is defined in there, is the sample size. And we have s squared. This is from chapter 2, I believe. The sum s squared is equal to the sum of xi minus x bar squared over n minus 1. And that is I equal 1 through n. This is s squared. So you may have some data, and you find the sigma square, or the s square. And the s square in here is the variance of a sample of size n. So it's the variance of a sample. It is not the variance of a population. So we have t distribution, and there is one thing that we need to pay attention to, which is the degree of freedom we're not talking about freedom of choice or freedom of, we're talking about the freedom in the degrees of freedom in statistics, but it's very similar. If you have, when we say the degree of freedom, the formula for that is mu or nu. This is called nu. Okay, nu is equal to n minus 1. That means if you have 10 people, the degree of freedom is 9. 9 people have the right to speak, 1 person does not. Why? That's how they defined it. In statistics, it's really, they give you, if it is 10, then it is 9, if it is 20, it's 19, and so on. But the main idea behind the degrees of freedom is not to consume everything, but to give the possibility of the person to choose certain parameters to work with. Then we have, basically this is all what we have, by the way. In part 6.3, we have this part in here, and this formula or this rule, if we want to say that the degree of freedom is equal, is in u, and is equal to n minus 1. We will find the degrees of freedom later on when we use the tables, because we'll have to use some tables in here. Sampling distribution of the variance, where there is a chi distribution, um, 6.4, and it states the following: if s squared is the variance, then there is a certain parameter which is chi. I don't know how to write that exactly, but it's not x for sure. It looks like x, but it's not x. Square this is equal to n minus 1 s square over sigma square, and is equal to the sum of xi minus x bar over sigma square. This is from I equal 1 through n. So this thing here is chi. So that's how it's pronounced, chi. Chi square distribution. You may not need it now, but if you are doing a research that deals with, for example, you're doing your dissertation, you're working on a very, very serious project of research, you will have to work with this also. You'll have to use it as a chi. And there is chi alpha. The chi alpha is equal to, it's not really, there is no sign, but if you look at it, it's like this in a way. So it starts from 0 and it goes like this, where this is our alpha in here, and this is fx square and chi square, not x, chi square, and this one here is chi square n, and here the 0. So the chi square is considered as the variable. As I said before, we will not gonna be using it except in certain situations. So if there are two variances, and we have two parts, and we have two variances, then we will be using the F distribution. The F distribution is S1 square F. This is the F distribution. F is equal to S1 square over S2 square, where S is considered the variance of the first parameter over the variance of the second independent random sample. So if there are two random samples, S1 and S2, with S1 and S2, then we can use that F to find the relationship. At last we may look at the last part. Well, we're going to use an example. So the distribution of the variance, presentation of the normal theory distribution. Okay, we have table 4. If you have the book, I'd like every one of you just to turn the pages to that table 4, just to see what's going on in there. Table 4. So in here, table 4 is used to find the values of T distribution. Okay. As T alpha where the area under curve under the T curve is equal to alpha. The shaded area, the shaded area under the curve, the shaded area under the curve. Okay, forgot the word shaded in here. So here is the curve. This is our mu in here, and we have the t, f of t, and we have t in here, same as f of x and x. And in this part in here, we have alpha. So this is alpha. And this place here is t alpha. Now, so we have nu. We said nu is equal to n minus 1. That's the degree of freedom. And we said that the degree of freedom, as if n is 30, then it's a large sample. So for alpha greater than 0.5, no need to tabulate. No need to tabulate T alpha. We don't need to use the table for it. T 1 minus alpha is equal to negative T alpha. These are some of the rules, and this here is the symmetry property. You may have used that in high school, symmetry property. Let me just continue of T distribution. For nu equal infinity, we have z 0.025 equal 1.96 and is equal to t 0.025. So this here is table 3 on page 515, and this one here is table 4 on page 516. So this here is the last line. You will find this value in here on the last line, and this value here you will find it on the 4th row, 7th column. That means that T and Z, as we said before, T and Z are interchangeable. Z is when we know the population's standard deviation or variance. We use T when the population is large and we cannot use the standard deviation for the population. So let's just quickly take a look at table 4. So table 4, it has table 3, table 4, it has the T alpha, and we have the degree of freedom. So we have the nu and we have the alpha, and some of the problems I think assigned, they use that. They use alpha and they use T. Okay. All right, we have the last part is for this chapter. The last part we may try to solve some problems, but I'm going to do that. I think that's basically that's it for this chapter, except for the preparation. Normal distribution, I don't think that it's really that. Well, let's see how we're going to be dealing with it. I'm not sure that we're going to be using that much, but I would like to. I'd like just to try to take a look at one of the examples that use the table, just to make sure that, because we're going to be using the tables, all the tables 4, 5, 6, and so on in this chapter, all of them will be used in here. So it's good that we know how to use that, unless you think that you can do it on your own while doing the problems. The representation of the formula is really, I'm not really in pressure to do it. Mainly when you see the square root of the square root of the square root and so on and so forth. So you prefer, probably we prefer just to hold on to it, read it, picture it, take a picture with your eyes from that book, think about it. How can you use that formula? Believe me, I did not use it personally, and I don't think that there are people who use it in our level. So it's better that we look at it, but we're not going to be so fan of using it. All right, so let's quickly look at. We have some problems that we want just to look quickly at them. There is the one on page 190. The sampling distribution of the variance. The lower one, not the top one. You can look at the top one, it's okay. Yeah, the top one, it gives us, let's look at that. On page 190. Page 190, there are two examples, the top example and the lower example. You don't have the books. Okay. So in here, they have an optical firm purchases glass to be ground into lenses, and it is known from past experience that the variance of the refractive index of this kind of glass is 1.26 times 10 to the negative 4. As it is important that the various pieces of glass have nearly the same index of refraction, the firm rejects such a shipment if the sample variance of 20 pieces selected at random exceeds 2.0 times 10 to the negative 4. Assuming that the sample values may be looked upon as random sample from a normal population, what is the probability that a shipment will be rejected even though sigma square is equal to 1.26 times 10 to the negative 4? So in here, they have the chi-square, and they use the chi-square, the formula for chi-square, n minus 1 times s square over sigma square. So they already gave you sigma. They already gave you the s square, that is the 1.26, I'm sorry, 2.0. And sigma square is given 1.26, and the just calculation, direct calculation. However, even if we don't look at that, and we use directly, we go directly to the table using chi-square, and we have chi-square for 0.05 is equal to 30.1. We go to table 5, and you know table 5 is on page 525, no, it's 517. 517, that's table 5. Table 4 is 516, table 5 is 517. So it's chi-square and the degrees of freedom. So chi-square of 0.05, chi-square is 2.05 from table 19 degrees of freedom. If we go there, 19 degrees of freedom, okay, you will find 30.144, okay, 30.144, that is, do you see that? If you look at the column of alpha equal 0.05 and you go all the way down up to nu is 19, you will see that it's 30.144. In here, they have 30.1. So if we go to 30.44, we find that, you know, thus the probability that a good shipment, if erroneously be rejected, is less than 0.05. That means alpha is 0.05. So the error, we said before that alpha is the error. And if we're looking at chi-square, we get the alpha from the table, because we don't know which alpha that is. The next example, we use table 6. So we have alpha, and we use table 6, and table 6 is page 18, 518. And again, you have the degrees of freedom and the degrees of freedom. So you have V1 and V2. There are now nu1 and nu2. There are 2 samples, so you have nu1 and nu2. You may want to check that one. The essential is that table 6 is for 2 types of samples, sample 1 and sample 2. Table 5 is just for 1 sample. The other table, table 7 and so on, we did that before, and I believe that that's where we are. So, any questions? Did you get anything?
Let's take that test.
Take the test. All right. So, yeah, I think we're there. Okay, so we stop here, and there are those problems. Please go over the examples mainly when trying to solve the homework problems, and it will be very helpful that you have that. If you have any difficulty or anything like that, just shoot me an email, and I'll try to do my best to give you the answers. Okay. All right. Okay, thank you so much, and have a good night.